Hi guys, welcome back to our discussion on infinite series. In today's video, I'll talk about power series. So to start, let me discuss about the objectives of the study. So at the end of this lesson, you should be able to number one, understand the definition of a power series. Second, find the radius and interval of convergence of a power series. Third, determine the endpoint of convergence of a power series. And the last but not the least, differentiate and integrate a power series. Okay, do you know that an important function like e to the x can be represented exactly by an infinite series called a power series? Like, for example, the power series representation for e to the x is written below as e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on and so forth up to plus x to the n over n factorial plus and so on and so forth. And as you can see, for each real number x, it can be shown that the infinite series on the right converge to the number e to the x. Like if the value of x is 1, then e to the 1 is 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial plus and so on and so forth up to plus 1 to the n over n factorial plus and so on and so forth. Okay, so from this representation, let us now define what a power series is. So if x is a variable, then an infinite series of this form, summation of a sub n x to the n, where n is from 0 to infinity, is equal to, if n is 0, then you have a sub 0. If n is 1, then you have a sub 1 times x to the 1 or a sub 1x. Plus, if the value of n is 2, then you have a sub 2x to the second power, and so on and so forth. So this series is called a power series. And more generally, an infinite series of this form, summation of a sub n x minus c quantity to the n power, where n is from 0 to infinity, which is equal to a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c quantity raised to the second power plus and so on and so forth, is called a power series centered at c, where c is constant. Okay, so as an example, so letter A, the given series here is centered at 0. So we have the summation of x to the n over n factorial, where n is from 0 to infinity. That if n is 0, then you have x to the 0 over 0 factorial is 1. If n is 1, then you have x over 1 factorial or x. If n is 2, then we have x squared over 2 factorial. If n is 3, then you have x cubed over 3 factorial, and so on and so forth. Okay, the next example of a power series is centered at -1. So we have the summation of -1 to the n times x plus 1 to the n power, where n is from 0 to infinity. That if the value of n is 0, then you have -1 to the 0 is 1 times x plus 1 raised to 0 is 1. So that's the first term. Okay, next. If n is 1, we have -1 to the n, or sorry, -1 to the 1 is negative, and x plus 1 raised to 1 is x plus 1. So we have negative x plus 1 as the second term. And then if n is 2, then we have -1 to the second power, that's positive 1. And then x plus 1 quantity raised to the second power, and so on and so forth. Okay, the last example is a power series centered at 1. We have the summation of 1 over n times x minus 1 quantity raised to the n power, where n is from 1 to infinity. That if the value of n is 1, then you have 1 over 1 times x minus 1 raised to 1. So we have x minus 1 as the first term. If n is 2, we have 1 over 2 times x minus 1 raised to the second power as the second term. Plus, if n is 3, we have 1 over 3 times x minus 1 quantity raised to the third power, and so on and so forth. So from the previous slides, we can say that C always lies in the domain of the function. And from theorem 9.20, it states that the domain of a power series can take three basic forms. So we have a single point, an interval centered at C, or the entire real number line shown in this figure. Okay, so let us discuss Theorem 9.20, which talks about the convergence of a power series. For a power series centered at C, precisely one of the following is true. That number one, the series converge only at a single point, which is C. And the number two, there exists a real number R greater than 0, meaning positive, such that the series converge absolutely for absolute value of x minus c is less than R, and diverge for absolute value of x minus c is greater than R. And then number three, the series converge absolutely for all x. So this number R is called the radius of convergence of the power series. If the series converge only at C, then we can say that the radius is 0, or R is equal to 0. But if the series converge for all x, then the radius of convergence is infinity, or R is infinity. Okay, the set of values of x for which the power series converge is called the interval of convergence of the power series. Example, suppose we are asked to find the radius of convergence of the summation of n factorial times x to the n, where n is from 0 to infinity. So the first thing that we have to do is we need to check now whether the given power series converge at its center. So the center is at x equals 0. So we need to evaluate the function at its center by replacing all the x variable of this power series by 0. So we have the summation of n factorial times x to the n. But because x is 0, so you have 0 raised to n, where n is from 0 to infinity. That if the value of n is 0, then you have 0 factorial is 1, and 0 raised to 0 is 1. So 1 times 1 is 1 as the first term. But if n is 1, then we have 1 factorial times 0 raised to 1 is this is 0 times 1 factorial is 0. If n is 2, so 2 factorial is 2, while 0 to the second power is 0, and any number multiplied by 0 is 0. So the succeeding terms, the values are all equal to 0. Okay, so this indicates that the power series converge at its center at x equals 0. Next, we need to check whether the series converge or diverge for some value of x. Let's say for any fixed value of x such that the absolute value of x is greater than 0, we let the n term of this series as n factorial times x to the n. And then to check whether the series converge at this specified value of x, we need to use the ratio test for absolute convergence. We evaluate the limits of the absolute value of u sub n plus 1 all over u sub n as n approaches infinity. But u sub n plus 1 can be obtained from u sub n by replacing all the n variable by n plus 1. So from here, we get n plus 1 factorial times x raised to n, where n is n plus 1, all over u sub n, where u sub n is n factorial times x raised to n as n approaches infinity. But n plus 1 factorial can be written as product of n plus 1 and n factorial, while x to the n plus 1 can be factored as x raised to n times x. And as you can see, because n factorial and x to the n are common, so we can we can cancel this out. Okay, so we can cancel this out. Sorry. Okay, and same with x to the n. So we have x and n plus 1 as the remaining factors. Then by taking the absolute value of x, we have here this absolute value of x times the limits of the absolute value of n plus 1, which is n plus 1. And to evaluate the limits of n plus 1, we replace n by infinity. So infinity plus 1 is infinity. And infinity times the absolute value of x is still infinity. So this indicates that the series diverge for the absolute value of x is greater than 0 and converge only at its center. And therefore, the radius of convergence is r equals 0. So in summary, for a power series centered at C, precisely one of the following is true. That number one, the series converge only at C. Number two, there exists a real number R which is greater than 0, such that the series converge absolutely for absolute value of x minus c is less than R, and diverge for absolute value of x minus c is greater than R. And then number three, the series converge absolutely for all x. So we let R here, the radius of convergence, and if the series converge only at C, then the radius is 0. But if the series converge for all x, then the radius of convergence is infinity. Okay, the set of values of x for which the power series converge is the interval of convergence of the power series.